All right, good morning. Welcome to week 5. All right, any questions to start things off with? Yeah. All right, well, let me start by talking about the midterm. So your midterm is Wednesday. It's scheduled during class time, so it'll start at 10 o'clock Wednesday morning, and you will have 55 minutes for the exam. I posted an announcement over the weekend with some important details about the midterm. We touched on these in the beginning of the term, but I want to reiterate these before Wednesday because if you don't know these details and you figure them out Wednesday, it's going to be too late. So, main thing to know is first of all, your answers to the exam have to be handwritten. You're not allowed to use any electronics during the exam except to download the exam from Canvas, to scan your answers, and to upload your answers. All right, the exam will be posted on Canvas under the midterm section. It will be a PDF file, and you can download it or look at it, in Canvas. And so you're allowed to do that during the exam. You should write your answers out on paper and then scan them, save them as a PDF, and upload those through Canvas. And so if you have not done this, if you've done CSE215 with me, which pretty much everybody in this class should have, you've been doing this for homework assignments. If you've done other classes with me, you've done this. So make absolutely sure today that you know how to do this. And if you don't, come to office hours tomorrow and let's go through your technology and figure out how you can capture pictures and upload them as a PDF. Do not try to figure this out for the first time on Wednesday, because Wednesday is when you're taking the exam. You're doing programming questions, you're answering questions about hash tables and such. That's not when you want to be messing around with Microsoft Word, save as a PDF, and all that kind of junk. Figure it out now. Okay. And then during the exam, you're allowed to use 6 pages of double-sided notes or 12 pages of single-sided notes. And those notes can be pretty much anything you want. They can be handwritten, they can be typed, they can be computer printed, but you need those notes to be on paper because you're not allowed to use electronics except for these 3 things described up here. So you should be making notes throughout the course based on going back and reviewing your notes from class, working on assignments, and so on. So you should have something pretty close to your note sheet at this point. So 6 double-sided pages, 12 single-sided pages, and you basically get that, paper, something to write with, and whatever you need to read, the exam questions, save them as a PDF and upload them. And that's it. Now you're on your honor on this. I'm not at the point yet where I'm going to have you use webcams. Everybody's on their honor to follow this, and there will be an honor statement printed at the top of the exam, and you need to read that. And then at the top of the answer sheet you turn in, you need to write the words that say you agree to the honor statement, and then sign your name next to it. Any questions about that? That's just procedural stuff. But let's nail this down right here and now and make sure everybody knows this and is able to do this so that we don't have to worry about this, for the next 2 days, and we can concentrate on questions about, data structures.
No notepad.
No, gotta write things by hand.
Oh, brutal.
It's what would happen if we were in person. I would hand out, an exam with pieces of paper on it, and you would write your answers on there. And so we're sticking with that model. You do not need to print the exam and fill it in there. In fact, there's no space on the questions to write the answers there. So just write your answers on your own paper and upload those.
I have a question.
Okay.
Will we be in the Zoom call while that's going on?
So I recommend being in Zoom because inevitably, you know, there's typos or things I you know, forget to mention or specify or something like that. And as soon as somebody points that out, I'll put something in chat saying, you know, question 3, make sure you do such and such. And I'll usually mention something on my microphone to that effect. If you're not in Zoom and there's something that makes no sense, right, you might end up wasting 10 minutes trying to do something that's impossible. So I recommend being in Zoom and just kind of you know, keep it in the background. People's microphones will be muted, and if I need to tell you something, I can do that. Is there a way to take the exam at a different time? There is not. It's scheduled during class time because there should be no other obligations during that time, because that's when class is normally held. So it's got to be 10 o'clock. And it's 55 minutes, so you have 10 o'clock till 10:55. Yeah, you might want to see if you can leave like a few minutes early. The entry on Canvas will not lock at 10:55, even though that's when the exams are due, for 2 reasons. One, some people have an extended time allowance, and 2, if you know you turn your exam in 5 seconds late, I'm probably still going to accept it. If I have Canvas lock you out at 10:55, then you wouldn't be able to turn it in even a few seconds late. But if you turn it in more than a few seconds late, it's at my discretion whether I'm going to grade it or give you a 0. So make absolutely sure you turn it in on time based on what Canvas considers to be on time.
It's going to be straight to a 0, no 10% knockoff or whatever.
I'm very much trying to mimic the in-classroom experience, which would be, you know, I'll you know, generally expect exams to be turned in when, you know, I've announced time up, and I'll generally walk around the classroom and, you know, pick up exams from people who are still working on them. And if somebody won't give me their exam, well, you know, that's the end of the class. I'll leave, and that's a 0. So so yeah, I don't want to get into a calculus of, you know, 10 points per minute or this or that. Just turn in what you have by 10:55. And you can upload multiple times, so you know you can scan your answers and upload them, you know, at 10:30, and then keep adding to your document as you write more answers, and do another quick upload at 10:50, and then do your final upload at 10:55. Because you know everyone's going to be trying to upload at the same time, so there's bandwidth issues and all that good sort of stuff. All right, other questions? All right, not a whole lot. Can we review hash tables? Sure. It's not a whole lot to say about topics. Basically, everything we've done up through, but not including trees, is fair game for the midterm. So certainly, you know, everything related to structures and using the structure statement in C, you know, defining a structure with different fields, accessing those fields when you have a pointer to the structure, which is using that arrow notation, and so on. So all of the mechanics around C and structures, allocating dynamic memory using malloc, freeing memory using free, checking for memory leaks with valgrind, debugging using gcc-g to link in debugging symbols, and then using GDB, basic GDB commands, all the stuff we've been doing in class and that you've probably been doing on your own when you're working on your projects. Make files, you know, what is a make file, what does it do, what are the components of it, what does a make clean option do, and so on. So all that stuff you should know, and you probably don't have to do a lot of studying for that if you've been using this stuff, you know, for 5 weeks now to write your programs and so on. It should mostly be stuff that's pretty fresh in your minds. Data structure wise, right? Definitely going to be questions on linked lists. That's been, you know, 2 of our 2 programming assignments so far. So the idea of a linked list, having nodes point to other nodes, why we do linked lists, why they're faster than arrays, why they're slower than arrays. The idea of a sentinel node and having a sentinel node that, you know, points to the first node. You've written bunches of code using linked lists, so you should understand that code really well. I will have you writing code on the exam. It's not going to be the same code you did for PA1 or PA2. But if you can write the code for PA1 or PA2, you should be able to write code for the questions I'll ask you on the exam. Stacks and queues, right? You should understand how those things operate, how they're set up, the idea of a LIFO and a FIFO, last in, first out, first in, first out. You should understand how to implement stacks and queues with linked lists, because that's PA2, but also with arrays. The idea of, you know, an array with a stack pointer for a stack, or a circular array with head and tail pointers for a queue. And then hash tables, and we'll review hash tables a little bit in a minute. But, you know, the basic idea of a hash table and a hash function, the idea of collisions and 2 ways of handling collisions. And that's our most recent topic, and it's topical to PA3, so I want to do a little bit of review on hash tables, just to make sure everyone's on the same page with those. And let me grab an attendance scan. So, you know, the basic idea of a hash table is we could make an array and set up a series of cells, you know, elements in our array. And in a regular array, this is just a plain old, you know, array of something in C. Your index to an element is an integer from 0 to the number of elements minus 1. And when we have a hash, what we want to do is we want to store a pair of things, which we call a key, and a piece of data. And the idea is we want to look like we're indexing with a key and storing data. And the way we make that work is we take our key and we run it through this thing called a hash function. And the hash function simply points to an integer between 0 and n minus 1. And so if I'm doing license plates, and I want to store a plate associated with, you know, AAA123, if my key is, you know, a string, I put my string into my hash function and it generates some number like 2. Okay, that says element 2 in this array, that's where I'm going to store my key and the data associated with it. That's really all a hash function, a hash table are, right? Hash table is just a way to store things with these non-integer indices. They could be integers, but they don't have to be, right? These things that index our data. And if we just stored, you know, a set of keys and a set of data and a pair of arrays, and we wanted to find the data that goes with some key, we'd have to search this whole array. And maybe we'd keep it sorted, maybe we just do a sequential search, right? But that's all pretty inefficient. And so instead of just having, you know, an array of keys and an array of data, we also have this function that if we put in a key, it tells us exactly where in this array we can expect to find that key. And we go right to that location, and then we can find the data. And so you might have questions related to coding this or coding some piece of this, or you might have conceptual questions, or you might have a picture of an array and be given key data pairs and asked to fill those in, or I'm not sure. Vitamins. And then the main complication with hash tables relates to collisions. So if you have key 1, which maps to, you know, hash of key 1, and you have key 2, which also maps to the same location, you can't store two keys in the same spot. And so you need some way to resolve this conflict that both key 1 and key 2 want to be stored in element 2 of this array. And so how do you resolve that? And there's two main approaches. There's probing, where we basically rehash. You know, we take the first key, key 1, we hash it, the spot's empty, we store it there. So here's key 1. And then later on you want to store key 2, and our hash function says, hey, it should go right here. You look and there's something in that spot. So we use a different hash function. And the way we do this is we basically add a second argument to our hash function, which we can call a probe number. And so we initially hash with a probe of 0. If we get a collision, we rehash with a probe of 1. And it kind of acts like a different hash function, right? It will take our key presumably to a different location. It may take it to a location down here where we've got some space. And if that spot's open, we store our key data pair there. If that's got a collision, then we need to rehash with a third hash function, and we do that by using a third value for our probe, say the value 2. And that should give us a yet different location to try to store our key. And if that spot's available, we'll store it there, and so on. And so we just keep going like this. And eventually, hopefully, you find a spot where you can store your key data pair. If there's nothing left in the table, if there's no space available, then your table is full, and there's not much you can do about that. The other approach to collisions is chaining. And we're going to talk a lot about chaining today because that's going to be what you do in PA3. And in chaining, basically, instead of actually storing the key data pair in here, you basically have an array of sentinel nodes. And what this entry 2 would be is a sentinel node that points to a linked list. And we'd put, you know, key 1 into that linked list, and then when we get another key 2 that points to the same location, we just add key 2, and so on. So you save all the keys that hash to this location in a linked list that's pointed to by that sentinel node. Let's see, easiest way to handle collisions is to provide a disclaimer. There's no collision provision, and the user of the software agrees to take all responsibility. Exactly. And if you let somebody else use your hash table and they're not on the contract, then there's no liability.
How much will we have to understand probing on the exam, because that is
pretty much what we just went through.
okay.
Do you want to go through an example of probing?
Sure. I get the general gist of it, but just I don't know. I just keep blanking.
All right, let's do a specific example. So let's hash addresses. So your address is going to be a number and a street and a city and so on and so forth. Let's make a hash table. We'll call it hash. And we're going to make 100 entries in our hash table. And our hash function is going to be your zip code modulo 100. Pretty terrible hash function because everybody in the same zip code is going to try to get stored in the same location. This is just begging for tons of collisions. But it's an easy example to work with. So bad hash function is just take the zip code mod 100. If we want to probe, we need a hash function that takes 2 arguments. So we're not going to use this. We're going to say, hash of address, comma probe equals, and let's do quadratic probing. Let's do zip code plus the square of the probe mod 100. All right, so let's have, and so we're going to have key and data. And so let's do Clark College. So Clark College, and I think their zip code is 98663. I could be wrong about that, but we'll pretend. All right. So the first thing that comes into your hash function is, hey, I want to store Clark College with a zip code of 98663. So out here at location 63, right? So we hash, 98663 with a probe value of 0. And so take the zip code, add 0 squared, that's 98663, modulo 100, that's 63. So our Clark College gets stored with, the address, 1933 Fort Vancouver Way, etc. All right. Now let's say you want to store, I don't know, Burgerville, and they're on the other side of the zip code boundary, so they go at 98662. So we hash them with a probe of 0, and 62 mod 100 is 62. So right here at location 62, we'd store Burgerville and their address. And there's, other stuff in this address, so these are unique. All right, so now we want to store, I don't know, let's do Geyser Hall. And that's 98663. So we try to hash 98663 with a probe attempt of 0. So zip code plus 0 squared mod 100, that's 63. And we look, and 63 is in use. So we're going to rehash with a probe value of 1. And so for this hash function, we take the zip code, we add 1 squared. So that's going to be 98664. Mod 100 is 64. And location 64 is free. So we store, this thing for Geyser Hall. And that's fine. Okay, now we're going to do McDonald's. And they're right by Burgerville, so they're 98662. So we hash 98662, 0, and we're going to get, 62. And 62 is already in use. So we're going to rehash 98662 with a probe value of 1. And that's going to be 98662 plus 1 squared is 63, modulo 100 is 63, and that's in use also. And so we're going to rehash with a 98662 and a probe value of 2. This is going to be 98662 plus 2 squared, that'll be 98666, and we'll reduce that modulo 100, we get 66, and location 66 is available, and so we'll store McDonald's at that index. And what happened was, you know, we tried to store something here, we got a collision. We tried to store it in the next location, we got another collision on the next attempt. We didn't go after the next sequential location, we jumped down 3 spots. And if that had been occupied, we would have jumped down another 5 spots, because we would have added 9, right? 3 squared to our initial key. And so, you know, quadratic probing is spreading out how far we jump on each successive probe attempt. But it's really just, you know, it's the same thing over and over again. We take our key, we take a number that we use to, you know, change the hash function a little bit or a lot, and we rehash and find a new index and we try to store. That's really the only difference from not having a probe function.
Okay. Thank you.
You're welcome.
That probe square thing will eventually run you through every possible combination in that hash table?
Well, it's a good question. It depends on the length of the hash table, and for some lengths I don't think it will. For some lengths I think it will start to repeat before you've tried every possible probe value. So picking a good probe function can be tricky, and it partially depends on the length of the table. This is why you find a lot of hash tables whose length is a prime number. But I'm not going to ask you to write a hash function based on data or something. Just kind of understand the basic concept of how you use it.
Cool, thank you.
Yeah, you're welcome. All right, other questions? I'm messing with my camera, obviously. I'm getting some horrible rasterization, and I'm not sure why. Because my resolution should be pretty good. Oh well, we'll live with it. All right, so questions you can expect on the midterm. There'll be some short answer, fill in the blank, multiple choice, those kinds of things. There'll be some programming questions. And as with, you know, 224, some questions may ask you to write a program, some questions may ask you to write a function, some questions may ask you to write a few lines of code. And be really sure you're not doing more work than you have to. If I ask for a few lines of code, don't write an entire main program with an argc, argv, and functions and parsing and all that kind of stuff. If I ask for an entire program, don't just write one line of C. So be really clear that you're doing the thing that's asked for in the question. And if you're not sure, right, I'll be in Zoom, just send me a chat message and say, hey. All right, let's talk about PA2. So PA2 is graded and turned in. There might be 1 or 2 that are still coming in, but most people have run out of slip days or used most of their slip days. So if I haven't seen PA2 by now, I'm guessing it's not coming in. But if you're using your slip days and you've got them and you're planning to turn in today, go ahead and do that. But general comments on PA2. So across the board, really good job with that assignment. In the end, it may have felt like it wasn't that much work, or maybe it did. But PA2 is pretty significant because it's really taking the idea of, I've got this data structure called a list, and I've got this interface to it, a init, add, search, that kind of thing. And you've modified it, and then you're using that to implement new data structures, right? Stacks and queues. And then you've got this interface to stacks and queues, and you've got a main program that uses that interface to interact with those structures. And if you kind of step back and look at what you've done, you've got this hierarchy, right? You've got a main program, PA2, and it's calling, stack this, queue that, and so on. And maybe you wrote those directly, or maybe you called, other functions that do link list things, and those are, written line by line in C. And so there's this whole hierarchy of functionality. And if you, had something else that needed to use stacks and queues, if you were writing a job management system for an operating system, right, you might call the queue functions to put jobs into the queue, take jobs out of the queue, and so on and so forth. And this is the main skill that we're working to develop throughout this CS sequence is tackling large problems by actually tackling smaller problems and putting together the solutions to those. And the way we tackle the smaller problems is by tackling even smaller problems and putting the solutions together. And we keep doing that until, the actual work you have to do is just kind of like, sit back and type a few lines, have some cappuccino, and you're done. So this is an essential skill. And PA2 looks to me like people are getting very good at this kind of breaking things into pieces and putting them together and so on, and that's fantastic. Main issues that I saw in PA2, there were some people who had some trip ups with deviating from the assignment. So for example, when you go into stack mode, you're supposed to print the contents of the stack. Not everybody did that. So little things like that, which, are not programming concerns. They're concerns with, reading a specification and implementing. And so that's, something you just learn through practice. But on the programming side, right, most people's code was pretty much spot on. And so that was really good. And I was actually really happy with what I saw in the submissions. Did you get extra credit for doing a tail pointer? No, but you get bragging rights. So that's good. What was my O1 solution? The main idea I came up with for doing a tail pointer was have your queue point to a little sublist, and have that sublist actually be the thing that has a tail pointer stored in it and a sentinel node. Well, now that I'm saying that, I'm wondering if there's a problem with that.
I was thinking you could probably just rather easily just store the address of the tail in your main program, right?
You can't really do that, because then you're what if you want to have 1,000 queues? You would need to have 1,000 tail pointers in your main program, and you'd have to tell the user, hey, by the way, when you use my queue package, you also need to keep a variable around in your main program, and that's a totally different interface to the queue system. So, and it's kind of like a global. Say again?
Can you store it in, like, perhaps the data value of the Sentinel?
So some people did that, and that works, and we're lucky that it works, because on this particular operating system, your Q node is 16 bytes. Your first 4 bytes are the data. Your second 4 bytes are unused, and then your last 8 bytes are used for the next node. So you happen to have 8 bytes up here because of this packing. But if you did this on an older 32-bit system or a 16-bit system, these might be stored next to each other, and the whole node would only have 12 bytes to it. And so you might not be able to do that without clobbering something.
I see.
All right, so PA2 is good. And I've posted grades and feedback, and if you have questions about that, definitely come by office hours, and we can go over it. If you're at a point where you don't feel like you got PA2 working, or you kind of got it to work but you don't feel confident about your solution and so on, definitely come by office hours tomorrow and let's go through it, because you really want to understand linked lists for sure, structures, all that kind of stuff, and stacks and queues. But the stacks and queues are sort of secondary. And people who had difficulty with PA2, I don't think it was about the stacks and the queues themselves. I think it was mostly about the mechanics or the concept of linked lists, and building on top of those. So definitely come by and let's go over whatever questions you might have had, or ask them right now if you want, because this is totally fair game for a lecture. All right, well, let's go on with PA3 then. So, so PA3 is posted, and it's due a week from Friday, so you have almost 2 weeks for it. And it's going to be a long assignment. It's going to have a lot of parts and pieces, and it's probably going to take a while to figure out exactly how to do it. And the fun thing about PA3 is once you figure it out, and once you've got the pieces in place, it's not a lot of code. There's going to be a lot of machinery you have to build. There's going to be a lot of writing functions and such, but those functions may only have a few lines of code inside. And it's figuring out exactly what you want to put in those few lines of code that becomes sort of the main challenge for this assignment. You're going to be putting together a number of different data structures. In particular, you're going to be putting together a hash table, which will be built on top of an array, and using a hash function, which will be a pretty simple, C function with a loop in it. And then you're going to be using linked lists, because we're going to be chaining for collision management, and you're going to have a linked list with a sentinel node stored in each location in the hash table. And if you continue, doing this in kind of a hierarchy, have your main program which calls a series of hash functions, and your hash function calls a series of list functions, right? You can get away with doing relatively little work in the end. But it's going to be really important that we keep these firewalls in place, and in particular, our main program is going to interact with the user, and it's going to interact with a hash, and the hash is going to interact with a linked list set of functions, and the linked list functions are going to interact with Unix doing things like malloc and so on. And as long as we keep things in a hierarchy, right, your main program is never going to say malloc. Your main program is never going to think about sentinel nodes, right? It's going to talk to the hash package through a series of well-defined hash functions. And your hash functions will talk to, you know, the linked list package, and they're not going to worry too much about mallocing. They're never going to malloc linked list nodes, right? They're not going to worry too much about sentinel nodes. That's going to be managed by the linked list. And the linked list is going to do the down and dirty work of, you know, making a sentinel node and looping through until you get to a null pointer and all that kind of stuff. And this is the kind of thing where usually when people start getting in trouble, it's because their main program starts trying to, you know, do things with a linked list or do things with mallocs and frees and sentinel nodes and things like that. And so we want to think clearly about this hierarchy. And the way the assignment is written, I sort of spec out functions that I want you to develop that will support this breaking down of functions into different categories like this. So here's PA3 as it's posted on Canvas right now, and this is fairly lengthy. It's a 6-page write-up, but it's got a good amount of detail. So let me give you the high-level view, and then let's look at some sample code, and then we'll start digging into the details of this. The high-level view is you're writing a program to manage a database of license plates. Okay, just like we've been using in our examples in class. So the main key in our program is a license plate, which is a collection of symbols. Usually it's, you know, some letters, a dash, and some numbers, but there are vanity plates also, so it could be just a set of letters and so on. Don't make any assumptions about what constitutes a license plate other than what you find in the assignment. So our key is a license plate, and the data is a name, which consists of a first name and a last name. And so it's 2 pieces of data, right? Don't put them together as a single string. Keep these 2 pieces separate, first name and last name. And then that pair of data items is associated with a license plate, a key. And so the program you're going to write is basically going to do the following. It's going to read a database of license plates and names from a flat file. And /temp/database.txt is your sample temp file. Your sample database file. It's going to read in that license plate information and basically let the user type in a plate, and it will print out information about that license plate, namely the first name and last name that it's associated with. And that's the main behavior of your program. So you run it, it initially reads all this data into memory, it builds a hash from it, and then the user types in a license plate and it prints out the information that it finds. And that's probably enough to jump into a demo. So the sample executable is under /temp and it's called plate. And it needs at least one argument, which is the database. And it takes a second argument that's optional, which is the size of the hash table. If you don't specify a hash table size, it defaults to 100. But you got to specify a database. So the sample database is tempdatabase.txt, and this is just a flat file with a plate, I think it's a first name and a last name. I don't remember. We'll check the assignment, but plate and the name. And then basically it asks you for a license plate, and I can type something like, let's do Dagny King. So let's put in the license plate GJK-185, and it tells me first name is Dagny, last name is King. So this flat file is plate, first name, last name. And if it says enter plate and I say PKM-884, it tells me that belongs to Rosa Maxwell. If I say PKM-885, it tells me plate not found. And pretty much anything I type in, it's going to take it as a license plate. And then there's a few exceptions. There are a small number of commands I can feed in to this program. And so the commands begin with an asterisk. And so I can say load, or I can say dump, or I can say dump followed by an integer. And these are not license plates. Anything else I type in, it assumes it's a license plate and it tries to look it up. But these three commands, which each begin with a star, have special behavior. And only these three commands. So for example, if I type, you know, star haha, it's going to assume that's a license plate lookup. And it's going to say, hey, you know, I don't find a plate called star haha. But if I do the command star load, that's not a license plate lookup. That's one of our special commands. What star load does is it shows me how populated the hash table is. Now our hash table is using chaining, so each entry in the hash table is a sentinel node of a linked list. Star load will tell me how long each of those linked lists are. So if I do star load, I see 100 entries, because my hash table has a length of 100, and the length of each entry. So there were 15 plates that hashed to index 0, and those are all stored in a linked list with 15 data nodes, and the sentinel node for that linked list is at the first element in my hash table array. There were 10 keys that hashed to index 1, there were 9 keys that hashed to index 2, and so on. So star load shows you how many plates are stored at each location. It's also a way to measure how many collisions you're getting. We've got 1,000 license plates in the database. We've got 100 entries in the hash table. So we would expect on average, 10 license plates to be stored in each entry. So these ones that are like 15 or 13 are longer than we would expect. But we got a few that are shorter, like entry 5, there's only 6 plates stored there. Can we use string.h on this assignment? Absolutely. All right, so that. Go ahead.
Was your hash function the same as you did on the probe?
It's written up in the assignment, so we'll take a look at that in a minute. But it's a form of quadratic hashing, quadratic probing. All right, so star load is one command. The other command is star dump, and there's two versions of star dump. Star dump displays the contents of each cell in the hash table. Star dump n displays the contents of a single cell. So for example, entry 88 has a length of 6. There should be 6 key data pairs stored in entry 88. So I can say star dump 88, and it shows me the 6 nodes stored in there. So these 6 keys, these license plates, all hashed to 88. And here's the name, and this name has to be last name, comma, first name. And that's critical, because it's the easy way for me to make sure that you didn't just store the name as a single string, that you actually stored 2 separate pieces of data, first name, last name. So when I ask for a plate, SGH891, I want to see the first name and I want to see the last name. And I want those to be, prefixed with this on separate lines. And when I do a dump, I want to see last name, comma, space, first name. All right, and if I just say dump, it dumps out the entire hash table. So every license plate in the database should appear here, and it's basically just doing a dump 0, dump 1, dump 2, all the way up through dump 99. And then end of file gets you out. X does not get you out. If you do X, it's going to think it's a license plate, and it's going to look for a license plate X. So if you want to get out, you have to use Control D, which is end of file, and that gets you out. And you should free all your memory and not have any memory leaks. So if I run the same thing, but I specify a hash table size of 1,000, now if I look at my load, a bunch of my cells are empty. A lot of my cells have one entry in them. A few have two. This one has four, right? But the length of our linked list is generally smaller. Because we've got 1,000 entries in our hash table, and we've got 1,000 license plates that we wanted to store. If this was a perfect hash function, every entry would be filled with exactly one license plate, but it's not perfect. So some entries, like 728, have 3 names. So I can dump 728, and there's the 3 names that hashed to that index. I can dump 993, and there's only 1 name that hashed to that index, 1 plate, and that was Venus Todd. If I look at 998, it tells me there's nothing stored in there, so if I dump that cell, there's nothing in there. All right, you want to do tons of error checking, right? If I say star dump 2.3, that's a license plate checkup. Oh no, that's weird. Huh, okay. I guess I'll accept 2.3, but not that. All right, so star dump, follow it with an integer. I guess I'm going to allow you to put in extra stuff after the integer, so that's fine. But if you say star dump followed by something that's not an integer, that's not one of your legal commands. Okay, your only legal commands are load, dump, or dump followed by an integer. So dump followed by haha, that's a license plate lookup. Right, that's a license plate lookup. That's a license plate lookup, and so on. And there's really no such thing as a syntax error, right? If you just type in something random, it's going to look it up as a license plate. Everything is, of course, case sensitive. So lowercase ZQS708 is different from uppercase ZQS708. And then Control D gets you out. All right, other questions on the behavior? We have to talk about the details, but the intended behavior, and you can run this sample program yourself. You can use it against that database, or you can make your own database, and you can use that to test it out. If I make my hash table 10,000 entries long, right, most of it's going to be empty. Occasionally, I'll probably find something with one plate hash to it. There's some 2s. So this does not look like a very good hash function because, you know, after about 8,000 some, it doesn't look like I used any of my hash table. Well, there's a 1 right there. But it's pretty empty at the end. Pretty empty in the beginning. And seems to get a lot of business in the middle. License plates and names can be stored with lowercase letters, strange symbols, you know, anything basically. But I won't go too bizarre on you. I won't go with like non-printable characters or tabs or things like that. But you should not have to make any assumptions about that. When you parse the database file, you should be able to use %s space %s space %s. Right? And the only thing you should have to assume is that there's no spaces inside the license plate or inside the first name or the last name. So just do your scanf with 3% s's, and this should pick up these 3 pieces. And then just don't deliberately do anything extra like, you know, convert case or look for special characters or anything. Just take them as strings.
Are we going to use the exact same database as that example?
You're welcome to, or you can make your own database. When you're developing it, it may be easier to work with a small database because, you know, you want to read something in and know if it ended up in the right spot. and working with 1,000 databases in the sample file is kind of a lot. So you may want to start with a smaller database file, and you may want to start with a simple hash function. You know, take the ASCII code of the first character or something. Or, you know, treat your license plates as numbers and just use the last digit, you know, for a hash that holds 10 things. In the write-up, I suggest, you know, working on simpler versions of this to begin with, and we'll talk about that in some detail. But, you know, you're presumably learning some new concepts here, right? This may be the first time you're coding a hash table. It may be the first time you're coding a chaining algorithm, and so on. And so, you know, you've got almost 2 weeks. Start simpler if you want.
I have a question. I don't know if it's mentioned in that assignment.
Yeah.
I read it, but when we create the chain link for each one, would we malloc for every single node right away, and then or malloc for every single like create a sentinel for every single entry right away, even if it might be empty?
We'll have to see if the assignment specifies, but my suggestion would be when you create the hash table, create all of the sentinel nodes. Because part of the idea of a sentinel is we don't have to worry about, you know, is this the first time we're putting something in the list? And if you create them on the fly, it might be a nice, you know, memory saving feature, but it's going to complicate your list code. So if it doesn't say you have to do this, I would still strongly suggest create all your sentinel nodes right in the beginning when you create the hash table.
Sounds good.
Cool. Right, parse your command line arguments as usual, so if it's not a valid hash table size, right? But you can have a hash table. Do I check for negative numbers? Yeah, hash size should be at least 1. But, you know, you can make a hash table with a single entry, and, you know, guess what? Well, all of my license plates are stored in one big long linked list now. And when I want to search for a license plate, I'm doing an order n search. I'm basically just going through that whole linked list looking. So, you know, here's a peculiar version of PA1 maybe, right? And if I dump cell 0, right, everything is stored in there.
What happens if you dump a cell that doesn't exist?
That should give you an error. So let's say I do this with, you know, 100. If I look for 100, it'll give me an error. If I look for -1, that should give me an error. And so if you run it through Valgrind, right, should get no leaks. So I did 4100 Alex, 4100 freeze, 64,000 bytes allocated. You can do a lot of calls to malloc in a lot of different places. But again, build this up in pieces. All right, so let's see. Behavior. Okay, so minor variations are okay. For example, if you say plate not found in uppercase or in lowercase and it's different from my example, I'm okay with that. But you know, barring very minor variations, I'm going to want you to stick to the description in here as closely as you can. So 2 ways to run your program: plate database name or plate database name and table size. Reading in the database, so there's no spaces, but make no other assumptions about the format. So you can use scanf with 3% s's to read in these 3 fields. And if you can't read the database, then you should print out an error. So if you do template, right, cannot open that file. Don't just try to open it and then get a seg fault when you start trying to read it in. So try to make your program as kind of bulletproof as possible. User interaction, pretty much everything the person types in is a license plate, and either print out the information or print out plate not found. And then those 3 special commands. All right, output details. Normal plate information when you do a lookup should be like this. First name colon followed by the first name, last name colon followed by the last name. When you say star load, print out, you know, entry, the cell number, colon, and its length. And just print those out in this format, please. Right? I don't care if you put an uppercase L on length or you put a space on either side of the equal sign. But I do care if you say entry 0 and you go down to a new line and you say this linked list contains 10 elements. And then you go down a new line and say entry 1. Because when I'm grading this, right, I'm going to run it with certain test cases and I'm going to expect to see, you know, a 10, 7, 12, 3, 10. And I'm going to run your code and be looking for that. And as much as I normally appreciate, you know, conversational code, I don't want you to force me to read a lot of conversational code when I'm trying to grade 40 or 50 of these. So that's the main reason I'm asking you to stick, you know, very close to this format. What's the chances of people with those names and license plates? So I generated this database at random, right? The plates are mostly letters dash numbers, and I used a random number generator to make those, and then I got a database of names, and I scrambled those and put them together at random in pairs to make first name last names, which aren't actually very good first names last names, because, you know, I don't know, maybe they are, but they're randomly generated, so any relationship to people, living, or person is purely coincidental, as they say at the end of good movies. And then star dump 3, tell me contents of cell 3, and then print it out in this format: plate followed by the plate, and then name, last name, comma, first name, and put delimiters around the plate, because if the plate, you know, happens to contain name colon, I don't want to be, you know, see confusion about that. And if there's nothing in the cell, right, just, you know, don't print anything. All right, you exit on end of file, so if you're reading from standard in, you should hit a Control D at the beginning of the input line to signify end of file. If you're reading by redirecting input from a file or from a command, when that file has no more input available or that command isn't generating any more output, that will signal end of file. And at that point, you want to exit after freeing memory.
The entire program enters or exits after Control D?
Mm-hmm. So let's talk about detecting end of file. And so far in your first 2 assignments, I've had to use an exit command, imaginatively X, to exit your programs. But, you know, X could be a license plate. It should be a license plate. So we exit by doing Control D. And the way to detect end of file, so you're going to be using fgets. And fgets, you know, takes some character array, some length, and standard in is what it's reading from. And this returns a file pointer. So if you look at the manual page for fgets, right, go down to the return value, returns the character read as an unsigned car cast to an int or EOF. Oh, that's for getC. Fgets returns S on success, that's the buffer, or null on an error or when end of file occurs. So fgets will return null if it hits end of file. And so you can say something like, you know, car status equals fgets, and if status is equal to null, then you've hit end of file, and you can do whatever you want to do. Call your code to free up memory, and then exit your loop or exit your program or whatever is appropriate. And so when I show you my code, sometimes you'll see this line. Something like this. All right, so what does this do? This calls fgets and says, read up to this many characters into this buffer from standard in. And if it succeeds in reading, at least one character, even if it's just the enter key, then this will return the value of this first argument, which is the address of my memory buffer, which will never be null. And so fgets will not be equal to null, and I'll go ahead and run the body of my loop. But if we're in this call to fgets and the user hits Control D, or the thing you're piping to has stopped generating output and so on, fgets will return null. This condition will fail. We will exit the while loop and come down here. And so if I want to do input in a loop and have that loop exit when the person hits Control D, I usually do something like this. And so you're welcome to take that approach, or just save the return value in a variable and do something like an if statement and maybe break out of your loop, or do this at the bottom of your loop and set a flag and check the flag at the top, or any of those usual tricks. Let's see, but it's not if Control D, it's just if Control D is the only input. Right. So if you do something like if I do haha and I hit Control D, that does not generate end of file. If I do a few spaces and I hit Control D, you gotta trust me, I'm hitting Control D there, that does not generate end of file. But if I'm at the beginning of my line and I hit a Control D, that will cause fgets to return null. And if you're picking that up in your code will say, oh, that's the end of the input from the user, and we can free memory and exit.
Why such a weird exit like X and null?
Say again?
Why such weird return values?
So I don't know why they decided to return the address of this buffer, because it always seems to me like you know what that is because you're passing it as an argument, and I suspect there's some other version either extending this or something that this is extended from where that makes sense, instead of just returning an integer flag or something. But I don't know what the history of that is or what the motivation was. But I pretty much never write fgets unless I'm write it like this, unless I'm just doing a one-off code. It's like peanut butter and jelly. They just kind of go together in my mind. But yeah, it's a good question. Let's see, license plate ID, format question. Are there any license plates in the randomly generated database that have a character, a number instead of a dash? Absolutely. License plate can be anything that does not contain spaces. And it can be anything except there's two license plates you cannot have, star dump and star load. Any other combination of characters that don't have any kind of space is potentially a valid license plate. And the database, the test database, contains a few of those that don't have dashes. All right, cool. So let's take a 5-minute break, and then let's dig into more of the details, and that should do us for PA3. So let's come back at 11:15. All right, see you back in a few. next couple of hours.
Okay. Do they need a contact?
No.
Oh.
They'll drop them at the door and run away, going, ah.
Yeah, that's quick.
Quick?
I said that's quick.
Yeah. You asked if I need contact?
If they needed someone to answer the door.
Oh, no.
Okay.
That's what I thought you asked.
Yeah, you're right.
You looked at me funny. They only had peanut butter Captain Crunch, so I didn't get it.
Ah,
So I got Cheerios.
excellent. No, I was just thinking I want $1,000,000.
You what?
You are doing wish fulfillment for me on such a regular basis.
Okay.
I want $1,000,000.
Cool. See what I can do.
Okay.
All right. PA3 Contrinued.
What's your thought on the the Russia and Ukraine stuff going on right now?
Oh, that's a nice light topic. Yeah, I'm gonna say beyond the scope of the course. Not that I'm dismissing it as unimportant at all, but pretty complex. All right, let's see.
Happened the first, but it won't be the last, probably.
Yeah. Yeah, I'm rewatching National Geographic's Genius series on Einstein, and that's fairly disturbing, given where the world is right now. So yeah, good stuff. Let's see. So dump command, exiting. All right. So implementation. So here's the gorier details on how you're going to make this all work. So you're going to do two data structures, a hash and a linked list. So your linked list nodes look like this, very similar to what you've done before. But there's going to be three data fields in each node. There's going to be a license plate, a first name, and a last name. And these are set up as car stars. Downton Abbey I have not watched. That sounds intriguing. Got a smile. And these have to be car stars, right? I do not want you to declare these statically, because if I say car plate bracket, 12, and someone has a license plate with 14 characters in it, your code would start doing funny things. Or if you find someone whose last name has 36 characters in it, and you said car last bracket 20, so make sure these are dynamically allocated as needed. We'll talk about that in a few minutes. So the node of the linked list contains 4 fields, 3 data fields, 3 car stars, plate, first name, last name, and then a pointer to the next node, which is just next. I've never used car plate bracket. I believe it will still work, and you can still use malloc, but I'll always do it like this in my examples and sample code and lecture. But if you want to figure out what car plate bracket does, and if that works, that would be great. And then you can teach me something. I don't know if there's a standard best practice. I usually see pointers set up like that. All right, so your linked list should include a sentinel node. Same as we've been doing. So that's your first structure, is your linked list. And, you know, pretty much works the same way that we've been doing, except you don't have to keep it sorted and so on. All right. And then there's a sentinel node. Sorry, and there's a hash table. So the hash table is an array of pointers to sentinel nodes. In other words, it's an array where each element of the array is a struct node star. And so this is the first place it can start to get a little funky. Each element in the array is a struct node star. So an array of these elements would technically be a struct node star star. And if you want to avoid that, I suggest you use a type def. Make a type def. You can call it hash entry, which is a struct node star. And then your hash table is just a hash entry star. And again, you can't just define, you know, this to be an array of 1,000 struct node stars, because we don't know how long we want this array to be. We want to allocate it dynamically at runtime. So you can't predefine the hash table size, and don't assume predefined sizes for the strings. All right, so hash table is an array. Each entry in the array is a struct node star, which is a pointer to a sentinel node. So the same thing we've been doing when we write this out on paper and we talk about chaining. All right, here's your glorious hash function. So you take a license plate, it's a character array, loop over all the characters, take the ith character, multiply by I plus 1 squared, add all of that up, reduce it by the hash table size. That should give you a number between 0 and hash table size minus 1. This thing right here will give you an ASCII code for the ith character. And you can use plate bracket I as an integer. It's a char, but it's actually a really short int, and it will cast automatically to an int. So if I just, you know, add that to a running sum or multiply it by I plus 1 squared, it will do the right arithmetic. So write yourself a hash function that takes an argument, which is a char star, that's your plate, and returns an int, which is this value.
So also to take in the hash table size?
Yes, it has to take in a hash table size, thank you.
So that'd just be a pretty simple loop where you just...
That's a straight for loop. Make a sum equal to 0, for I equals 0, I less than string length plate minus 1, I plus plus, sum equals sum plus I plus 1 times I plus 1 times plate bracket I. So it reads almost directly like the definition. Don't mess around with squares, just take I plus 1, multiply by I plus 1. If you try to use the POW function, you got to change the floating point and all kinds of weird stuff. So this is a weighted sum of ASCII codes. There's no built-in summation. This translates to like a for loop. So when we see something like this, initialize a sum to 0 and then write a for loop. I equals 0, I less than or equal to this, I plus plus, and add this to your sum inside the loop. And when you're done, your sum should be equal to your loop, to your sum value. You can reduce, you know, at the end, or if you're worried that you're going to blow up the size of an integer, you can reduce each time that you do this addition. Our ASCII codes are going to be, you know, nominally 100 or smaller, and so it would take, you know, a few 10 million characters before we'd start encroaching on what a 32-bit integer can store. So you're fine taking this modulo at the end of the addition, but you can always do it inside the loop if you have a different function that you're worried about overflow.
Oh, would the modulo of all of them added to each other equal the modulo of the end?
Yeah, isn't that cool? That's like the magic of modulos. You can do it along the way, or you can wait till the end and do it. So if you're doing this with pencil and paper and you do it along the way, your problem never gets too big. Whereas if you added, you know, a billion things, you might have some big long number, and then you got to do this big long modulo operation. So you can do it like inside here, and it also gives you the same value. I like modulos. All right. So the structure for your linked list nodes is described above. Your hash table is an array of pointers to sentinel nodes, each initialized to a different sentinel node of an empty linked list. So you're going to call your linked list init function, nominally 100 times, or however many times you have entries in the hash table. If you have 1,000 entries in your hash table, you're going to want to call the init function 1,000 times. And each time the sentinel node pointer that it gives you back, that gets saved in the next entry in the hash array. All right, so here's how you implement the hash table. You want a hash init function that takes one argument, which is a hash size, and returns a pointer to a hash entry. That's also how we return an array. So it's going to be the address of the first thing in that hash table. And then a function for adding to the hash table. So hash add takes 4 arguments. It takes the hash table itself, right, which is a pointer to a hash entry, and then 3 characters, character strings, the plate, the first name, and the last name. And what this does is, takes the plate, runs it through the hash function, gets a sentinel node, adds a new node into that list containing the plate, the first name, and the last name. And then hash find takes the same arguments, takes a hash table, plate, first name, and last name. It searches the hash table for that plate, and if it finds it, it does 2 things. It returns a 1 as a function value to say, I found the plate, but it also fills in these character arrays. So first should be pointing to something in memory that can hold a character array. It will copy the first name associated with that plate into this array. And then it'll copy the last name associated with the plate into that array. If the plate is not found, then it simply returns a 0, and it does not change the value of these. So if found, load the matching first and last name into first and last. Because we can only return one thing from a function, and we're returning an integer which says, 1 first we found it, 0 for we didn't, we also need a way to return the actual first name, last name. So we pass those back as arguments. So you pass in a pointer to a character array, and it will copy the first name and last name into those arrays.
I was wondering, I was like, how do you return?
So yeah, that's another funny part of this. All right, then make a function called hash load, which takes a hash table as an argument and prints out the load of each cell. So this is the function you call when the user types asterisk load. Just call hash load, pass it the hash table, and inside there you have your loop that goes through every element of the hash, figures out how long the linked list is, and prints that out. So in your main program, responding to a star load command is a single call. Just call the hash load function. Hash dump is similar to hash load. It takes the hash table, but it also takes a cell number. And it prints the contents of that cell. What does that mean? Go to that index in the hash table. You'll find a linked list. Print the contents of each node in that linked list. What do we mean by print the contents of each node? We mean print out the license plate part, print out the first name, print out the last name, format it the appropriate way. So if the person says star dump, all your main program does is call hash dump in a loop, which sets cell num to 0 and then 1 and then 2 up to the last cell number. If the person says star dump n, your main program just calls hash dump with a hash table comma n, whatever the value of n is. And then hash free takes a hash table and frees all the memory associated with it. And if you know the pointer to the hash table, you can get to all the memory that's been allocated. So when the user hits Control D, you detect end of file, you just call hash free, say goodbye, and you're done. So that's your interface between the main program and the hash table. Initialize, add, find, load, dump, and free. You can make extra functions if you want. and you probably will. All right, linked list. So our linked list looks similar to PA1, PA2, but a little more complex node structure. So list init creates an empty linked list, returns a sentinel node. That's just like init from PA1. List add takes 4 arguments. It takes a sentinel node and then the plate first name and last name. Add your data to the beginning of the list. Why? Because it's more efficient. We don't care about the order of the data in the list. When we search, we're just going to start at the beginning and search until we find it or run out of nodes. So the quickest way to add is to add to the beginning. And if you don't add to the beginning, your dumps won't come out in the same order as mine, and I'll think your code isn't working. So you'll lose points, and then you'll have to come to me and argue that it still works. So add to the beginning of the list. And so, what does this do? Well, it makes a new node. It copies plate first name and last name into the fields of the node. It changes the node to point to what the sentinel is pointing to and changes the sentinel to point to your new node, and you're done. List find takes a sentinel and then 3 pointers to characters. It looks for the plates, so start at the first node, move down the list, compare the plates. If you find a node whose plate entry matches the plate, copy that node's first name into here, copy that node's last name into here, and return a 1. If you get to the end of the list and you haven't done this yet, return a 0. So that's list find. List length is a function. You give it a sentinel node, it tells you how many data nodes there are. If the list is empty, it returns 0. If it has a single node, it returns 1. So what is this? This is a while loop, right? Set a counter equal to 0. Set a temporary equal to sentinel next, and while counter's not null, bump up your counter and move to the next node. When you hit a null, you're at the end of your list. Your counter tells you how many nodes you saw. List print prints the list contents in the right format, and list free releases all the memory associated with the list. Let's see, so for the add function, will it just add the data from the specified database we use? Yes. So when you start running your program, you're in the initialization, you open the database file, you read it with a series of calls to fgets, right, 1 line at a time, and for each line you're going to read a plate, first name and last name, and so you're going to hash the plate, find an index in your hash. At that index entry, you'll find a sentinel node. Now call list add with that sentinel node and the plate first name, last name from the database. When you get to the end of the database file, close it, and you're never going to need to call list add again. Now you go into the main user loop where the user types in a license plate, you call list find and print out the results and so on. Alright, list print prints the contents of each node in the list, and list free frees the memory associated. Alright, suggestions as usual, start early, as in today if possible. There are a lot of pieces here, and if you try to do this in a panic, it's going to get really muddled, and it's going to get really complicated. And if you are coding this without having a really clear image in your mind of how you're breaking this program up into different pieces, it's going to be a nightmare. It's going to be so many things doing so many different things and conflicting with one another, and an organizational mess trying to keep track of all those parts and pieces. It's going to make things really hard. So think about how you want to structure the program, right? And I've broken it out to you in a fair amount of detail on, breaking it up in functions, but think about what that means, right? Think about it from a pencil and paper perspective. Imagine reading in a line from a database file. What am I going to do? What's going to happen when I add this to my hash? What does that mean? Right? And actually visualize taking the plate, running it through a hash function, getting an index. Okay, I got an index of 7. What do I do with that 7? Well, if I go to element 7 in my hash array, there should be a pointer to a node. How do I add a new node to that? Well, I can, look at the next field, and I can play with sentinels and all that kind of stuff. But don't do that. Use your list link function, right? just call your linked list add function and say, here's a Sentinel node, here's some data I want to add, do it for me. And so when you're reading in your database file, you're not mucking around with, looping and changing pointers and all this kind of stuff. You're just going to call your linked list add function. When you see star load and you want to know how many entries are in, index 7, you're not going to start messing around with pointers and sentinel nodes and looping and bumping up counters and all that. You're just going to call your function list length. And inside list length, you're not going to be thinking about hash tables and star load and that kind of stuff. List length is a single loop. It's like your print function from PA1, but instead of printing, you're counting. And all it knows is it's getting a sentinel node, and it should return an integer. And what does list length do? It starts off with the thing the sentinel points to, a counter is equal to 0, and each time it goes from node to node, it bumps up the counter. When the node is null, it returns the counter. And this is a really, really good opportunity to think about modularization. What I said earlier about PA2 and how we had a hierarchy of functions and people are doing a good job with that, this takes that to a new degree, right? When you're writing this function, you're not thinking anything about hash tables, hash functions, command parsing, scanfs, nothing. You're just in a box, right? And your assignment today is, hey, I'm going to give you a sentinel node. Tell me how many nodes are in this list. And you write the code for that. You don't have to worry about how it's going to be used. Same thing with list print, same thing with list free. But then when you're writing, something like hash free, you don't have to worry about actually calling the free command. You're just going to make a loop that goes through every entry in the hash table, and each of those entries is a sentinel node, and you're going to pass that sentinel node to list free. And you're not going to worry how list free does its thing. You're just going to believe that if I take, entry 0 in my hash table and I pass that to list free, I've freed the memory for that linked list. I'm done. I'll go on to entry 1 and I'll do the same thing. I'll go on to entry 99 and do the same thing. That's it. I freed all of that memory. And then I'm going to have to actually call one free to free the array that I call, my hash table. But I'm not going to have to worry about how to free each of those linked lists. I'm going to use this function.
Question.
Yes?
So the main hash table itself is going to be a linked list, right?
No, the main hash table is actually an array.
But I thought we can designate the size of it. How do you do that?
So you're going to declare it to be a pointer to a hash entry. So let me do this with. So your hash table is going to be a pointer to a hash entry, and then you're going to use malloc. So you're going to parse your command line argument if it's present, or you're going to default to 100, and then you're going to, after you declare this, say hash table equals malloc number of entries times size of hash entry star. Sorry, times size of hash entry. So let me write that out.
Oh, yeah, I've never done malloc with array size.
Ah, cool, okay.
Linked list.
So let me copy this first. Alright, so we're saying your hash table should be a pointer to a hash entry. And then let's say, n equals length of hash table. So that defaults to 100, but if you have a second command line argument, you parse it as an int. That's what n is. So now we can say, allocate space for the array. So call malloc. N is the number of entries, and then each entry should be a hash entry. Alright, so your hash table is an array of n hash entries. So that's how much it takes to store one hash entry. This is how much it takes to store n hash entries.
I see. Okay.
All right. Yeah, we discussed the midterm as the first topic today. So if you go back to the video, it should be in the beginning, and it's tagged in the topic index. All right, so let's see. Suggestions: start early, don't start coding right away, make a plan. Right? So for me, one of the funnest parts of coding a large project is organizing it and thinking about what the parts and pieces are going to be and how they're going to fit together. And, you know, I might just, you know, grab a clipboard with some paper and just, you know, scratch out names of functions and draw some arrows for what's going to call what, or think about, you know, information flow, what information has to move from place to place in my program. Or I might start, you know, making a README, or I might start, you know, my one of my C programs and start putting in some comment blocks and start, you know, actually typing out the names of functions. But think about the organization of it, the parts and pieces. And then you have linked list codes. This should be PA1 and PA2, and you can definitely modify the linked list code you've done for this. You don't have to. And at this point, you know, that linked list code is probably something you can write from scratch pretty painlessly, because I think you've worked with it enough now that if you really just wanted to start over and make something to add a node to the beginning of the linked list, right, I don't think it's going to take you an hour to do that. But, you know, if you want to take your existing code and just sort of repurpose it, that's totally cool too. All right, and the main new piece here is the hash, right? So write a hash function, and you can test your hash function against the sample code, because, you know, if you run the sample program, and, you know, just pick a cell like 5. And all of these license plates hash to a 5. So if I take TWI-460 and run it through my hash function, it should come up with a 5. If it comes up with something different, then I'm doing something different. But that's, you know, kind of a detail that you can worry about later. If you can get this code to work perfectly for your own hash function, it's going to be, you know, a matter of just changing to the hash function from the assignment, and it should work perfectly compared to the sample program. So if you want to start off by tackling the hash function, you can do that. You can test it, you know, like this, see if these plates map to the right index and so on. But you can also totally just start with your own hash function and make life a little simpler. All right, and then think about how you're going to initialize the hash, which, you know, well, it's going to be something like that, right? Well, that's going to allocate the space for it. But then what do you have to do to actually make it into a hash table? Well, you have to, you know, hash table bracket 0 equals, and that should be the sentinel node of a linked list. Well, how are we going to do that? We're going to call list_init. And do the same thing for hash table bracket 1, hash table bracket 2, and so on. So do this in a loop. And do it from 0 to whatever the length of the hash is, -1. I guess we call that n. So from 0 to n-1, just set hash table bracket I equal to list_init. There's your whole initialization. The thing to think about is that, each time you call listinit, it should return a different value. It does the same thing. It creates an empty linked list containing only a sentinel that points to null, but it returns the address of that sentinel node, and each time you call listinit, it creates a different sentinel node, which corresponds to a different empty linked list. So this is going to store, n different values in these n locations in the hash table array. Double check that in GDB. Right? If all of these entries in here are exactly the same, there may be something wrong with your listinit function. Maybe you used a global variable somewhere to store the sentinel, and I didn't happen to catch it in my grading. So develop in pieces and keep checking along the way and make absolutely sure that what you're doing makes sense to you. And don't just do something because I said to do it. Right? What are you working on? I don't know. I'm calling listinit a bunch of times. Why? I don't know. Because I saw it in class. Make sure you know why you're doing what you're doing. And you may find shorter ways, more direct ways to do some of this stuff. That's always good. All right, think about initializing the hash and then adding entries to it. And there's two main pieces to this. There's reading the database file and building the hash table from it. And then there's getting a license plate from the user and searching for it. Good question. No, do not use malloc in main to initialize the hash table. Use malloc inside hashinit to initialize the hash table. And in main, just say, hash entry star my hash table equals hashinit parentheses, whatever your size is. And then this is the thing that calls malloc to make the array, and then goes through, a loop like this to set each entry in the array equal to a sentinel node. Cool. All right. So the most labor-intensive part, at least for the computer, is adding the license plate information to the hash table. All right. Adding to the hash is really just using the list's add function. So the only hashy part of this is, you want to add a license plate with this first name and last name. You use your hash function on the plate to figure out where the linked list is that you want to store this information in. If it says it's at index 218, you go to entry 218 in your hash table array. There's a sentinel node. Call the list add function with that sentinel node and the data you want to add.
I have a question.
Yeah.
So we have a search, right? So how does that search work? We search through every single. Do we search through the entire hash list for that license plate?
So let's see. And this is a good opportunity to break this into different pieces. So, search for ABC123. All right, so we hash the license plate, right? And it wouldn't be a quoted string, it would be a variable, obviously. But we hash that, we get an integer back that's an index. Okay. The sentinel node of the list containing this plate is hash table bracket index. Okay, that's the hashy part. We don't have to search 1,000 linked lists. We have to search one linked list. Which linked list? The one with this sentinel node. That's the hash part. So instead of searching 1,000 linked lists, we take the license plate we're looking for, run it through our hash function, we get an integer back. That integer is an index in this array. At that index, we find a single sentinel node. That's the only list we need to check. If this plate is stored anywhere in our hash table, it'll be at the list whose sentinel node is at that index. So we can find that sentinel node, and now we just have to search this list. And for that, we search it the same way we always search linked lists so far. We just start with the first node and just move from node to node. And that is an order n operation. And that's okay. In terms of implementation, though, our main program, our hash search function, are not going to do this moving from node to node to node. They're simply going to call the search function for the list. So they're going to call list find. Pass it the sentinel node, the plate you're looking for, 2 pointers to characters. If it returns a 0, then you can say, oh, plate's not found. If it returns 1, the name associated with that plate is stored in these variables. If you're doing this from the hash function, right, if you're doing a hash find, it doesn't print anything. It returns a 1 or a 0. If the plate was found, it'll return a 1, and the name is stored in here. If the plate was not found, it returns a 0. The main program, which called hash find, will see that 0 and say plate not found, or it'll see the 1 and it'll print out the first name and last name. So there's a lot of, passing the buck here. There's a lot of, tell me if this plate is found. And the hash function says, well, I don't know, tell me if the plate's in this list. And the list function is like, okay, I'll check the list, and it goes node by node by node. Alright, so the hash-related task is finding which node we want to add a plate to. Once you understand that, searching is exactly the same thing. Determine which list you're interested in, use that list search function. And then exactly the same thing for printing the contents of a cell. If you want to print, what's in cell 18, right? Well, hash table bracket 18 has a sentinel node. Use that with your list print function, and list print will print the contents of that list. Alright, hash load and hash dump are different versions of list printing. And we talked about that already. Freeing the memory will take some thinking about. But from the hash package perspective, all you have to do is free each linked list and then free this thing that you mallocked. Right? So this is inside hash init. So the hash free is going to free, each sentinel node. So iterate through your hash table, and for each one, instead of setting it equal to list init, pass that to the list free. And then when you're done, free the hash table itself. But the list freeing code is more complex, because our nodes look like this. There's a plate, there's a first name, there's a last name, and there's a next. And so our list free needs to free each of these nodes from memory, but before doing that, we need to realize that the plate and the first and the last are themselves pointers to memory that was mallocked. And so here's the second big wrinkle on all of this. You have to dynamically allocate space for all of these strings. Since we can't assume that a first name is always, 20 characters or fewer, when you need to create a node that has a first name in it, first you need to allocate space that's big enough to store that name. And then you're going to copy the name into that block of memory that you stored, and then this is going to have the address of that block of memory. So when I want to free this node, first I'm going to have to free the block of memory that the plate points to, the block of memory that the first name points to, and the block of memory that the last name points to. And then I'm going to have to move to my next node, and then I can free the entire block. So the freeing gets more complex.
Say you free, say you have the node, node arrow first.
Mm-hmm.
If you were to say, print that node arrow first, you would get, the name, how would you malloc that?
So node,
Free that, sorry.
how would you free it? Free node arrow first.
Really?
Well, so let's go ahead and look at mallocing. So to malloc, we'd say node arrow first equals malloc. However many bytes you need to store this string, which is going to be the length of the string plus 1, because you need to store the null terminator. So node arrow first equals malloc some number. That's how we create space for our string. And then to copy our string into that, we can use string copy. Copy into node arrow first, comma, first name. You know, where this is the thing you read out of the database. So this copies it into those bytes in memory. And in my print code, for example, when I find this node, if I want to print out the first name, I'll use node arrow first, which will have, you know, the first name that was stored in there. But then when I say free this, it'll basically release that block of memory that I malloced. So you might want to make a separate function in your linked list code called free node. Which frees a single node. And its job is to just free these characters. And then free the node itself. And then you could use your cleanup function from PA1, but instead of calling free, you would call, you know, my free or free node or something like that, which in addition to releasing the node, first releases the memory that each of those character pointers points to. And you can ignore this while you're developing, right? Memory leaks aren't actually a problem on Unix as long as your program exits after a reasonable amount of time. So you can completely ignore the question of memory leaks. Now, I don't recommend this in general, but, you know, for the sake of this assignment and for learning, you can ignore memory leaks up front. Deal with them later. Or be thinking about them and deal with them somewhat and try to finish dealing with them later and so on. But, you know, try to restrict yourself to like one small battle at a time. That's like a constant piece of advice I'm always giving students. One small battle at a time. So you know, fix one bug, take care of one syntax error, try to add one piece of behavior to a function. Instead of, you know, trying to write 500 lines of code that do everything and then start trying to make that work. Well, that's a really large battle, right? See, I had a weird syntax thing in PA2 where free node arrow first didn't work because char at temp equals node arrow first. Free node arrow first. As long as node arrow first is, oh, but it's a char star. I'd have to see your code to speculate on that. This is a chat comment on a weird syntax error from PA2. If char star temp equals node arrow first was not giving you a warning, then I don't know what your node structure was. But yeah, that sounds interesting. Some of what we do in C is trying to keep the compiler happy. It's not as bad as a lot of other languages, but sometimes we find ourselves doing things just because the compiler will be upset otherwise. But mostly C is pretty good about that. Alright, so freeing the memory takes piece. And then there's the main program. And again, you know, the main program, you can leave that for later, right? If you want to look at this from kind of like, you know, the bottom up, you can work on all of these functions without ever having a main program that looks anything like what's described in here, right? You can just call your functions from your own main program, and make a hash init of 10, right? And just call a bunch of hash adds to add some stuff. And then maybe go into GDB and see what your linked lists look like, and or start with a linked list package. Just make a main program that calls list init, calls list add a few times, calls list print. And that gets a lot of the details out of the way. That takes care of this whole dynamic memory allocation business, and tweaking your structures a little bit to work with these modified nodes, and so on and so forth. And then start working on the hash part. Don't get bogged down with the main program, because the main program has some weird parsing to it, right? And there's some stuff to figure out in there, but don't get bogged down with that. That's stuff that you can do, right? You wouldn't have gotten through 224 if you couldn't do that. So you can do it, have faith in that, and work on the stuff that's most new to you. And then when your brain is tired and you kind of want to break, go back and start writing some print a prompt and open a file, and go back and review how to read from a file using fgets and fopen and so on, and do the scanf business and write your switch statements and stuff like that. But don't spend half a week doing that before you've started thinking about hash tables, right? I suggest jumping into the newer parts of this, which are the hash table and the modified list structure. And in the end, once you get past the command line parsing, the syntax checking, the figuring out if they said star dump, star load, or something else, picking up end of file, once you get past all of that, your main program is really just calling a bunch of hash functions. Right? It's calling hash init in the beginning, and then hash add, hash search, hash load, hash print, and so on. So, start simpler, maybe don't worry about input errors, don't worry about command line options, and so on, and build it up. Right? Take things in small steps, start with something that you know and build it from there. Ask questions if you get stuck or you're not sure how to proceed. But definitely start this as soon as you possibly can. Right? There's a reason that you've got, almost 2 weeks to do this. It's not just because, I got ambitious and decided to post this assignment earlier. It's because this can take, close to 2 weeks to do, even if you're working on it pretty steadily a little bit each day. And if you work on this, an hour a day, it's going to take you less time than if you sit down in one day and try to get it done. Because there's just too many parts and pieces, and some of the stuff needs to sit with you for it to make enough sense to build on. Alright, and then upload tar file named PA3.tar, uploaded to Canvas. Your tar file should contain all of your source files, include files, and your well-written make file. To build an executable, the executable should be called main. I'm not giving you a detailed grading rubric here because there are so many parts and pieces to this. The easiest rubric is make your program work perfectly and you'll get 100. Okay? Yeah, that's the easiest goal to go for, because then you don't have to worry about, how much is this worth, how much is that worth. But, talk to me if you're running into trouble. Talk to me early if you're running into trouble, and we'll figure it out. Everybody can do this. Everybody can make this thing work perfectly. And I guarantee when you get on the other side of this assignment, you are in a much better place in your trajectory of learning computer science. Being able to do this, being able to break these things into pieces and use those pieces, and obey this abstract data type notion, will make this doable. But that's all we're going to do in 223. And that's what you're going to do, when you leave Clark, and that's what you're going to do in your job. And so this is a sort of really key exercise, a really key point in getting better with programming and being able to work on larger projects. And everybody is absolutely capable of doing this. Everybody in this class. So start it early, and if you're running into issues, come and talk to me, and we'll work through them, and then upload to Canvas. All right, questions. Other questions. There's been lots of good questions already. Follow-up questions on the midterm.
We have so many assignments due on the same day.
What do you mean?
We have like the GDB quiz, then another quiz, then I have 2 midterms.
Oh. Well, I can't help you with the 2 midterms, but well, yeah, I can because I got 2 midterms on the same day. But the quizzes, the dates I put on the quizzes are just kind of like, everyone should be able to do it by this date. But I definitely don't suggest you do those on the due date or right before the due date. Do them as soon as you're able to do them. Someone pointed out the quiz is actually due during the midterm. I think it's due at noon or something. But that's, I'm not expecting you to work on the GDB quiz while you're doing the midterm. And if, go ahead.
Actually, the GDB quiz is due 1 minute before midnight.
Oh, okay, cool. Okay, good.
The other quizzes do it like 5.
Really? Okay. I don't think I had a reason for that. I think it's probably a typo. But whenever I set it for, that's fine. Like I said, I didn't think too much about the due dates for the quizzes because I just sort of set them like, I'm planning to cover hash tables this week, and so by this day, we should be done with this and this and this. So I put the due date for the quizzes then. Because schedules change as we go through, but I thought those would be safe dates in the future, basically. If you're in my 215 class, yeah, we have a 215 midterm the same day, and that's either unfortunate or very good, because it gets it all over with, and we'll see how it works for my grading side of things. But I didn't want to do an exam when a programming assignment was due also. Yeah, no, that's cool. Not worried about it. But I've had other people who have asked me, why this is due on this day and so on. So yeah, they weren't magic dates. All right. Well, so we started talking about trees, and we've got like 3 minutes left here. So I don't want to start talking about trees again on top of all of this. So I'm going to let you out 3 minutes early. We'll do the midterm 10 o'clock on Wednesday. I'm giving you 55 minutes for the midterm, and then we'll do a break, and then the second half of class we'll go back to talking about trees. If you have extended time for the midterm, then you just want to watch the lecture afterwards because it'll be recorded and posted, and we'll be talking about trees. All right, so have a good one. I will see you in 2:15, or I will see you in office hours, or I'll see you Wednesday. Thoughts on the deposition of the King of Bavaria in 1918. I think I've already talked about that in class multiple times, so go back and listen to the lecture video. No, not kidding. I am kidding. All right, cool. Have a good one. I'll catch everybody next time.